I'm Greg Foot.
And I'm Fran Scott.
And this is the House of Sound.
Yeah! We're going to investigate the sounds of music.
And find out how all different sorts of sounds are made.
Sounds like these, this music. It's called Connect It, and it was written by a modern composer called Anna Meredith.
So as you can see, we can all make musical sounds just by using our bodies.
Yeah, and we can clap, obviously.
Yeah!
Yes, we can. Or we can sing.
No, you can't. Or we can play musical instruments like a clarinet.
But first things first, what is sound?
And how do we hear it?
Well, pin back your ears as you're about to find out with this little film I made. So Greg is over there having a little bit of a snooze, but I think there's something I can do about that.
Yeah, ha ha, very funny. OK, look, let's slow things down a bit and see exactly what was happening there. Sound is a type of energy made by vibrations. And vibration is the word we use to describe something that's shaken backwards and forwards really quickly. When any object vibrates, it causes the air around it to move. You can't see this happening because it's tiny things called molecules that are doing the vibrating. The molecules bump into each other, passing the vibrations through the air. This is called a sound wave. If your ears are close to the vibrations, then you hear them clearly. The further a sound wave travels, the weaker it gets. So because I was very close to Fran's gong, the vibrations were really strong, and so the sound it made was loud.
We can't actually see sound waves, but we can imagine what they look like. If I drop this pebble into this paddling pool of water, then you can see little rings of waves moving outwards over and over again, getting smaller until they run out of energy. And something else about sound waves is that big things vibrate slower than small things. Slow vibrations make a low musical note, whereas small things like this triangle vibrate more quickly and make a higher note. We call this pitch. So slow vibration means low pitch, fast vibration means high pitch.
Lovely. I've seen enough of that gong. Can you take it away? The thing is, sound waves can travel through anything that can vibrate, like air, or metal, or water. Sound travels faster through water than air, and even faster through metals like steel. What the sound travels through is called a medium. In fact, sound needs a medium to travel through, otherwise there's no sound. Fran, did you know that because sound travels so well through water, whales can sing to each other across a distance of up to 800 kilometres?
Whoa.
That is so far. It's the distance between Scotland and Iceland, or the entire length of Italy.
But look here, look at this demo that I've got that will prove that sound needs a medium to travel through.
OK.
This is an experiment that was first carried out hundreds of years ago, made famous by this scientist, Robert Boyle.
Nice hair.
It's good, isn't it? Believe it or not, in this big jar there is an electric bell ringing, but we can't hear it because we've taken out almost all of the air out of the jar using this machine here called a vacuum pump. And now it's called a vacuum pump because it pumps out the air to make a vacuum. And a vacuum is what we call a space where there is no air. And because there is no air for the sound waves to travel through, we can't hear the bell until I remove this pipe and let the air back in. So, that sound now, that's the air coming back in, but wait. And there.
Yeah.
That's really cool, isn't it? And so this reminds me, you know in those space movies where you hear those big explosions going off and they sound a bit like this?
Yep, I know them very well.
That is not actually how they'd sound. Instead, they sound like this.
What? Silent?
Yep.
Well, that's ruined some of my favourite films, hasn't it? Cheers. So sound needs a medium to travel through. And to be heard, sound waves need to reach some ears and a brain. Because sound is all about vibration, we need to do a little vibrating of our own to hear it.
Yep. Why don't you explain that while I build a giant human ear?
OK. Listen up, you lot. Sound waves are collected by your outer ear and travel down your ear canal. When those vibrating air particles hit your eardrum, it starts to vibrate too. Behind your eardrum are 3 little bones. The first is called the hammer, and it's connected to your eardrum. The next one's called the anvil, and it's connected to the hammer. The third is called the stirrup, and that's connected to the anvil. When the eardrum vibrates, the hammer hits the anvil. The anvil hits the stirrup and sends those vibrations on into your inner ear. This is a very special part of the inner ear called the cochlea. It looks like a snail and it's filled with liquid which flows over lots of tiny little hairs. The vibrations shake the liquid and that makes the hairs wiggle. These hairs are the start of something called the auditory nerve. How the hairs move depends on the sound being made, and the auditory nerve, which is a little bit like a wire connected to a computer, sends the information to the brain, which turns it into the sound we hear. So, Fran, how's your giant ear going?
So this cake tin here is like our outer ear, so this bit, and then we've got the cling film, which is like the eardrum, and then this cup and straw represents the hammer, anvil and stirrup, those small bones, and they go into this bowl, which represents the cochlea. And so this is the liquid inside the cochlea.
Okay.
So when we make a vibration here, it should go all the way down and make the liquid vibrate.
Got it?
Now, I'm going to hit it, and my hand is going to represent the moving sound wave, right? And let's see what happens.
Yeah, OK, it kind of works. Yeah, I mean, it looks great. You could, however, have just asked me and used this one that I made earlier. Much more realistic. No?
No.
OK, bottom line, sound is all about vibrations, and you don't need a musical instrument to make those vibrations. You can use bits of your body.
Just like these guys.
Oh, yeah.
You up for it?
Of course.
Right.
Yeah! Yeah!